In unsupervised learning, the situation is fundamentally different. There is no explicit target output. Instead, the model must define its own notion of what constitutes good structure in the data. This typically involves assumptions about the data distribution, such as clustering structure, low-dimensional manifolds, or compressibility. Because there is no ground truth label guiding the optimization, unsupervised learning objectives are often indirect. For example, in clustering, the objective might be to minimize within cluster variance. In dimensionality reduction, it might be to minimize reconstruction error. In density estimation, it might be to maximize likelihood. This indirectness makes unsupervised learning both powerful and tricky. It allows models to extract patterns without human labeling, but it also introduces ambiguity. The model may discover structure that is mathematically valid but not useful for the downstream task you care about. To make this more concrete, consider classification under supervised learning. Suppose you want to detect fraudulent transactions. You collect a dataset where each transaction is labeled as fraudulent or legitimate. The model learns decision boundaries that separate the two classes. Performance is easy to measure using accuracy, precision, recall, or area under the ROC curve. Now imagine you remove the labels and attempt unsupervised learning. The model might cluster transactions into groups based on spending patterns. Some clusters may correlate with fraud, but others may reflect geography, customer demographics, or merchant categories. The discovered structure is real, but not necessarily aligned with fraud detection. This illustrates a key limitation: unsupervised learning finds structure, not necessarily the structure you want. Another important difference lies in data requirements and economics. Supervised learning depends heavily on labeled data, which is often expensive. Labeling typically requires human annotation, domain expertise, quality control, and ongoing maintenance. In many real-world systems, data labeling is the dominant cost. Unsupervised learning, by contrast, can leverage vast amounts of unlabeled data. Raw data is usually abundant and cheap. This scalability advantage is one of the main reasons unsupervised and self-supervised approaches have become central in modern AI. They allow models to learn useful representations from internet-scale corpora without manual annotation. However, this advantage comes with trade-offs. The signal-to-noise ratio in unsupervised learning is often lower. Without labels, the model must infer what patterns matter. As a result, unsupervised objectives sometimes learn features that are statistically meaningful but not task-relevant. To understand how these paradigms behave during optimization, it helps to think in terms of gradient signal quality. In supervised learning, the gradient is directly tied to the prediction error. If the model misclassifies a cat as a dog, the gradient explicitly pushes the model toward features that distinguish cats from dogs. In unsupervised learning, the gradient signal comes from proxy objectives. For example, an autoencoder learns to reconstruct input data. The gradient encourages faithful reconstruction, not necessarily semantic understanding. The model may focus on low-level features like texture or frequency patterns rather than high-level concepts. This is why unsupervised representations often require further fine-tuning with supervised signals. The unsupervised phase builds general-purpose features, the supervised phase aligns them with specific tasks. Modern AI pipelines frequently combine these paradigms in multi-stage training. Large language models are a prime example. During pre-training, the model uses self-supervised learning by predicting masked or next tokens. This stage is technically unsupervised because labels are generated automatically from the data. After pre-training, the model undergoes supervised fine-tuning using human-labeled instruction datasets. Finally, reinforcement learning from human feedback may further refine behavior. This layered approach reflects an important insight: unsupervised or self-supervised learning is excellent for building broad representations, while supervised learning is excellent for task alignment and precision. Another dimension to consider is sample efficiency. Supervised learning can be very sample efficient when high-quality labels are available, especially with modern architectures and transfer learning. A relatively small labeled dataset can produce strong performance if the model starts from good pre-trained representations. Unsupervised learning often requires much larger datasets to produce high-quality representations because the learning signal is weaker. The model must infer structure purely from statistical regularities, which typically demand scale. Evaluation methodology also differs significantly between the two paradigms. In supervised learning, evaluation is straightforward because you have ground truth labels. You can compute metrics directly and compare models objectively. In unsupervised learning, evaluation is more nuanced. Clustering quality, for example, can be measured with internal metrics like silhouette score or external metrics if labels exist for validation. But often the real test is downstream usefulness. A common practice is to evaluate unsupervised representations by training a small supervised model on top and measuring performance. This is sometimes called linear probing. There is also an important conceptual distinction between generative and discriminative modeling. Supervised learning often focuses on discriminative models that learn the boundary between classes. Unsupervised learning often involves generative modeling, where the goal is to model the data distribution itself. However, this is not a strict rule. Some supervised methods are generative, and some unsupervised methods are discriminative in spirit. Historically, supervised learning dominated many practical applications because labeled datasets were available for specific tasks like image classification or speech recognition. However, the rise of deep learning and internet-scale data shifted the field toward unsupervised and self-supervised pre-training, especially in language and vision. One subtle but critical point for technical audiences is inductive bias. Unsupervised learning relies more on architectural assumptions and objective design. This means that the choice of model architecture plays an even larger role in unsupervised settings. For example, convolutional neural networks encode spatial locality assumptions that make them effective for image data even without labels. Transformer architectures encode sequence modeling assumptions that make them effective for text pre-training. Without such inductive biases, unsupervised learning would struggle much more. There are also hybrid paradigms that blur the line between supervised and unsupervised learning. Semi-supervised learning uses a small labeled dataset together with a large unlabeled dataset. The model leverages unlabeled data to improve generalization while still anchoring learning with true labels. Weak supervision uses noisy or heuristic labels instead of fully curated ones. Self-supervised learning generates labels automatically from the data itself. Self-supervised learning deserves special attention because it has become central to modern AI. The key idea is to construct a supervised style objective where the labels are derived from the input data. Predicting the next word in a sentence, predicting masked pixels in an image, or predicting whether two image patches belong together are all examples. This approach combines the scalability of unsupervised learning with the optimization stability of supervised learning. From a systems engineering perspective, the choice between supervised and unsupervised learning affects the entire ML lifecycle. It influences data pipelines, labeling workflows, model monitoring, and retraining strategies. Supervised systems often require ongoing label collection to handle distribution drift. Unsupervised systems require careful validation to ensure the discovered structure remains meaningful over time. In safety-critical applications, supervised learning is often preferred because performance can be measured more directly. In exploratory data analysis or representation learning, unsupervised methods are often more appropriate. Another practical consideration is interpretability. Supervised models trained for specific tasks sometimes produce more interpretable outputs because the objective is aligned with human-defined categories. Unsupervised models may discover latent structures that are mathematically coherent but semantically opaque. As AI systems continue to scale, the trend is toward heavy reliance on self-supervised pre-training followed by targeted supervised alignment. This reflects the economics of data. Unlabeled data is abundant, human labels are expensive, and the most powerful systems exploit both in complementary ways. If you step back and view the landscape, supervised learning is about precision under guidance, while unsupervised learning is about discovery without guidance. Modern AI does not treat them as competitors but as cooperating stages in a larger learning pipeline. For a highly technical practitioner, the most important mindset shift is to stop viewing the distinction as binary. Instead, think of a spectrum defined by how much explicit supervision is available and how directly the loss function encodes the desired behavior. Most state-of-the-art systems live somewhere in the middle of this spectrum. Understanding where your problem sits on this spectrum, and how strong your available supervision signal really is often more important than the specific model architecture you choose.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.